Hey everybody, and welcome to our second Real Analysis 2 lecture. Today we're going to be talking about limit points of a sequence. And let's start off with the definition. The real number p is a limit point of the sequence a sub n exactly when for every epsilon greater than 0, the interval p minus epsilon, p plus epsilon, contains infinitely many terms of the sequence. So let's look at a bunch of examples and play around with them just so that we get a fairly accurate idea of what it means for a real number p to be a limit point of a sequence. Let's consider this example to start off with. The sequence whose nth term is 1 over n. So our terms are 1, a half, a third, a fourth, a fifth, a sixth, a seventh, 1 over n, dot, dot, dot. One thing that we notice about these terms is that each succeeding term is smaller than the other. More specifically, each term is closer to 0 than its predecessor. 1/4 is close to 0 than a third. 1/3 is closer to 0 than is a half, and so forth and so on. So let's draw a picture here. And here's the first one. Here's our first term, 1 over n, or 1 over 1. Our second term is 1/2. And our third term, 1/3. Our fourth term is 1/4. And our fifth term, let's say 1/5. And then the sixth term, 1/6. And notice that these terms, again, are getting successively closer to 0. Here's the first term, here's the second term, here's the third term, here's the fourth term, here's the fifth term, here's the sixth term. And so first of all, we're going to look at this sequence and say, you know what? This sequence converges to 0. We're sure of that. And let's just make that observation. And how do I know that? First of all, this interval, 0 minus epsilon, 0 plus epsilon, which is exactly the same thing as negative epsilon, epsilon. This interval contains all but finitely many terms of the sequence 1 over n. And maybe we should show that. Notice that we can choose a natural number n such that 1 over n is less than epsilon. This would be the same thing as choosing a natural number n that's greater than 1 over epsilon. So for every natural number greater than n, the nth term of the sequence 1 over n is in this interval 0 minus epsilon, 0 plus epsilon. As a matter of fact, the only terms of this sequence that might not be in the interval these are the only terms of the sequence that might not be in the interval from 0 minus epsilon to 0 plus epsilon. Finitely many of these terms, right? The first point that we're making is this sequence converges to the limit 0. But we knew that anyway. Now let's take this a little bit further, okay? we noted that the sequence converged to L equals 0. And the way that we showed that the sequence converged to L equals 0 was by showing that this interval contained all but finitely many terms of the sequence. Now, we have another claim to make. Since only finitely many terms of the sequence, specifically 1, 1/2, 1/3, all the way to 1 over n minus 1, since only finitely many terms, these terms, are outside the interval from 0 minus epsilon to 0 plus epsilon, the rest of the terms of the sequence, 1 over n, 1 over n plus 1, 1 over n plus 2, so forth and so on, the rest of the terms of this sequence, infinitely many of them, 1 over n, 1 over n plus 1, dot, 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 all the way to infinity. The rest of the terms of this sequence, infinitely many of them, are contained in this interval. So, this interval contains infinitely many terms of the sequence 1 over n. Which means that if we let p equal 0, then p is also a limit point of this sequence. And in just a minute, I will state that in general terms. Here's a statement that generalizes the result that we just observed. Given a sequence a sub n that converges to a limit L, the real number L is also a limit point of the sequence. So every convergent sequence converges to its limit L, and that limit L is also a limit point of the sequence. And we'll establish that quickly. So we'll let the hypothesis be given. This sequence converges to a limit L. So for every epsilon greater than 0, the interval L minus epsilon, L plus epsilon, this interval contains all but finitely many terms of the sequence a sub n. So there are only finitely many terms of this sequence that are not in that interval. But the sequence consists of infinitely many terms. So if only finitely many of the terms fail to be in this interval, where are the rest of them? They're in this interval, infinitely many of them. And that tells us that L is a limit point of the sequence. So if a sequence converges, the limit of the sequence is automatically a limit point of that sequence. And I guess we may be tempted to ask the converse. If P is a limit point of the sequence, does it mean that that sequence converges to the limit point? And we'll look at an example to try to figure out the answer to that question. Here's a nice example. Consider the sequence where the nth term a sub n is given by negative 1 to the n times n plus 1 over n. And let's acknowledge first that the negative 1 to the n just serves the function of changing the sign of each term alternately from negative to positive, negative to positive. So the first term is negative 1 to the first, or negative 1, times 1 minus 1 over 1. So the first term is negative 0. The second term, negative 1 squared, is 1, times 1 over 2, 1/2. And then after that, notice that the numerator of each term is 1 minus the denominator, and the signs change. So we're going to get 1/2, negative 2/3, 3/4, negative 4/5, 5/6, negative 6/7. Another way that I could say this is after the second term, the sign changes for each term, and numerator and denominator increase by 1. So again, we have 0, 1/2, negative 2/3, 3/4, 4/5, negative 5/6, 6/7, and so forth. And let's draw these things on the graph down here on the x-axis. Right here, this is a sub 1. A sub 2 is 1/2. So a sub 2. A sub 3 is negative 2/3, so right about here. And a sub 4 is 3/4, so here's a sub 4. A sub 5 is negative 4/5. So let's see, maybe right here. Yeah, it's a good estimate. A sub 6 is 5/6. So if we cut this in thirds and then cut it in thirds again, so maybe about here, a sub 6. And a sub 7 is negative 6/7, so maybe right around here. And a sub 8, now what would that be? 7/8. So here's 1/2, here's 3/4. So here's a sub 8. And so on. And notice that the terms of even subscripts, A2, A4, A6, A8, are heading toward 1. And the odd subscripted terms, 1, 3, 5, 7, are heading toward negative 1. So the terms with the even subscripts are heading in one direction. The terms with the odd subscripts are heading in another direction. And let's make an observation. Let's see. I will claim that P1 equals negative 1 and P2 equals 1 are limit points of our sequence. Now let's see. How would we prove that? The even subscripted terms, we'll call them a sub 2n. And let's see, what are our even subscripted terms? 1/2, 3/4, 5/6. Okay. And we'll choose 2n. Let me stop and think about this for a second. Okay, I'm back. It took me a while, but I found my brains. So here's what we said. We want a sub 2n to be in this interval, given epsilon greater than 0. And saying that a sub 2n is in this interval is the same thing as saying that a sub 2n is greater than 1 minus epsilon and less than 1 plus epsilon. And what is a sub 2n? A sub 2n is 2n minus 1 over 2n. So this is the same thing as saying that 2n minus 1 over 2n is greater than or equal to 1 minus epsilon, which is less than or equal to 1 plus epsilon. And that's the same thing as saying, let's see, what did I do here? What incredibly brilliant step did I take here? I know, I subtracted 1 from all 3 sides. So if I subtract 1, this becomes negative epsilon. This becomes positive epsilon. And this becomes 1, let's see, 1 plus 1 plus 2n minus 1 over 2n, which is less than epsilon. Well, you know, a minute ago when I said I found my brains, I lied. Let's see. Going from this inequality to this inequality, what do I do? I'm going to subtract 1 from each side. Oh my goodness, have mercy on me. I subtract 1 from each side. Isn't that right? Let's see, I had a 1 here and now I don't, so I subtracted 1 from each side. And so I'm going to rewrite this -1 as -2n over 2n. And we have -1 plus 2n minus 1 over 2n. So this is a plus. Good gravy. And so what does that leave us with? -2n plus 2n is 0. So that leaves us with -1 over 2n is between negative epsilon and positive epsilon. And this thing is negative, so I guess I could say this. Negative epsilon is less than -1 over 2n, which is less than 0. And then I could say that when I multiply both sides by -1, 0 is less than 1 over 2n, which is less than positive epsilon. And this is what I want to key in on. I want to key in on that. And I'll multiply both sides by 2n, I guess. Okay. So 1 over epsilon is less than 2n. And exactly what does that tell us? If 2n is greater than epsilon, the term a sub 2n is in this interval. The only even subscripted terms and I'll write that as a sub 2n minus 2. So the only even subscripted terms that might not be in this interval are a sub 2, a sub 4, a sub 6, all the way to a sub 2 sub n, a sub 2n minus 2. Finitely many. Therefore, the interval 1 minus epsilon, 1 plus epsilon contains infinitely many And let me make up for something else that I should have done, but I didn't. I assumed that a sub 2n was in this interval and arrived at the conclusion that 2n was greater than 1 over epsilon. Now, I didn't actually go back and show that if 2n is greater than 1 over epsilon, that it turns out that a sub 2n is in this interval. So what I'm going to do is acknowledge that all of the steps that I took from here down to here are reversible. Let's see, if 1 over epsilon is less than 2n, then that tells us that 1 over 2n is less than epsilon. And since n and epsilon are positive, that means that they're both greater than 0. And then I can multiply all three sides by -1, and that will give me this inequality. And then I can reason, since -1 over 2n is less than 0, -1 over 2n is also less than epsilon, since epsilon is positive and greater than 0. And then what can I reason from there? I can reason that -2n over 2n plus 2n minus 1 over 2n is the same as -1 over 2n. And then I can reason that I can take this inequality and replace -2n over 2n with -1. And then I can take this inequality and add 1 to all three sides and get this inequality. And then I can just replace 2n minus 1 over 2n with its generic representation, a sub 2n. And that's the same thing as saying this term, which is contained between this term contained between 1 minus epsilon and 1 plus epsilon, is the same as this term being contained in the interval with endpoints 1 minus epsilon, 1 plus epsilon. So the steps that I took to get from here to here are reversible. And what that means is that for 2n greater than 1 minus epsilon, we have a sub 2n in this interval. So the only terms of the sequence that might not be in this interval are those terms with subscripts less than a sub 2n. Now, let's also show that p equals -1 is a limit point, and I will try to do this one a little bit more elegantly. So now we look at -1 being a limit point of the sequence. And so we have to show that for each epsilon greater than 0, the interval -1 minus epsilon, -1 plus epsilon contains all but finitely many odd subscripted terms of the sequence -1 to the n minus 1 over n. And this is a sub n. So in other words, what we're really trying to show is given epsilon greater than 0, -1 to the 2n minus 1 times, let's see, I substitute 2n in here for n. So 2n plus 1 minus 1, 2n over 2n plus 1 is in the interval -1 minus epsilon, -1 plus epsilon for all but finitely many n. And if I simplify this, that means given epsilon greater than 0, negative 1 to the 2n plus 1 times 2n over 2n plus 1 is in this interval for all but finitely many n. So here's what I'm going to do, and I guess I'll take a different approach for this part of the proof than I did for the previous one. I'll hit the chicken switch right away here and just call this scratch work. So given epsilon greater than 0, we want a sub 2n plus 1 to be in that interval. And that's the same thing as saying we want negative 1 to the 2n minus 1. Well, negative 1 to the 2n minus 1 is always going to be negative 1, so I'm just going to say negative 1. So we want negative 1 times 2n over 2n plus 1 to be in this interval. Negative 1 minus epsilon, negative 1 plus epsilon. And let's see, that's true if and only if, what do I want to do here? Oh, I know what I want to do. I want to say negative 1 minus epsilon is less than negative 2n over 2n plus 1. And that in turn is less than negative 1 plus epsilon. So this is just saying that negative 2n over 2n plus 1 is between negative 1 minus epsilon and negative 1 plus epsilon. And did you catch this? This should be a negative 1 here. Okay. Now, I guess what I want to do is just add 1 to all three sides. So that'll give you 1 minus 2n over 2n plus 1. And that's going to be yes, add 1 to all three sides. So negative epsilon is less than 1 minus this thing, which is less than epsilon. And now I'm going to combine these two terms with a least common denominator, namely 2n plus 1. So I'll replace 1 with 2n plus 1 over 2n plus 1. So I just rewrote 1 in the form 2n plus 1 over 2n plus 1. And now I'm going to combine these two terms and something really nice will happen. I'll get negative epsilon less than, and what will that be? 1 over 2n plus 1, which is less than positive epsilon. And n and epsilon are both positive. So essentially that's going to mean that 1 over 2n plus 1 is greater than 0. And that's less than epsilon. Now, what does that say about n, or 2n? That we want 2n plus 1 to be greater than epsilon. Okay. And by the way, here's where my scratch work ends. So to see this, we'll just let the hypothesis be given. Let epsilon greater than 0 be given. Let 2n plus 1 be greater than 1 over epsilon. This is true by our hypothesis. So what does that mean? We can divide both sides by 2n plus 1 and multiply both sides by epsilon. And since both are positive, the sense of the inequality stays the same. And since negative epsilon is less than 0, I can write this. Okay, so it looks like I have something trapped within an interval already. Looks like I'm on my way. And now I'm going to take this thing, 1 over 2n plus 1, and write it in terms of the nth term of the sequence, or maybe I should say the 2n plus first term of the sequence, negative 2n over 2n plus 1. And what is this thing? 2n plus 1 over 2n plus 1? It's equal to 1. So I'll rewrite it and acknowledge that fact. And now, since I'm trying to get the nth term in this interval, I'm going to add 1 to all three sides, and that will give me 1 minus epsilon here. It'll give me, I'll subtract 1 from all three sides. That'll give me negative 1 minus epsilon here, negative 1 plus epsilon here. So this statement means that this thing, negative 2n over 2n plus 1, is contained in the interval with this endpoint and this endpoint. So negative 2n over 2n plus 1 is in the interval negative 1 minus epsilon, negative 1 plus epsilon. And what is negative 2n over 2n plus 1? Isn't this just a sub 2n plus 1? So I'll write that. A sub 2n plus 1 is in the interval negative 1 minus epsilon, negative 1 plus epsilon for all n such that 2n plus 1 is greater than 1 over epsilon. These are the only terms that might not be in the interval -1 minus epsilon, -1 plus epsilon. And again, there are only finitely many. Specifically, at most, there are 1, 2, 3, 4, 5. At most, there are n minus 1 of these terms that are not contained in this interval. All the other odd subscripted terms, infinitely many, are in that interval. Earlier, we showed that P2 equals 1 is a limit point of this sequence. We just got through showing that P1 equals -1 is a limit point of this sequence. So this sequence has two limit points. Let me ask you something. Could either of these two limit points, or maybe both, be a limit of the sequence? What do you think about that? That we have two limit points of this sequence. Could either one of those, or maybe both, be a limit of the sequence? What do you think? Well, what's one of the things that we know about the limit of a sequence? Isn't it true that the limit of a sequence, the limit of a convergent sequence, is unique? Another way we can say that is the limit of a sequence, if such a limit exists, is unique. So if the sequence does have a limit, there can only be one. So I guess we know that it's not true that both of these limit points are limits of the sequence, because the limit of a sequence is unique, or a limit of a sequence is unique. So could maybe one of these two limit points be a limit of the sequence? Now, that's a question worth writing down. We'll acknowledge what it is that we've established so far. Are either or both of these limit points, P1 equals -1, P2 equal 1, are either or both of these limit points a limit of the sequence? And we've observed that P1 and P2 can't both be limits of the sequence, because a limit of a sequence, if it exists, is unique. So let's ask another question. Could either one of those be the limit of the sequence? And I'm going to answer no. And I'll explain why in just a minute. I think we're good to go here. We can answer this with a very brief explanation. Could either of these two limit points be the limit of the sequence? And we answer resoundingly no. And to do this, let epsilon equal 1. Now, if either one of these limit points were the limit of the sequence, then this interval for all values of epsilon, all positive values of epsilon, would contain all but finitely many terms of the sequence. Now let's see what happens. Epsilon equal 1 is given. And so the interval -1 minus epsilon, -1 plus epsilon is the interval 2, 0. Well, that definitely contains a lot of terms of the sequence. It contains infinitely many terms of the sequence. And to be more precise, it contains all of the negative terms of the sequence. So let's see, what does it contain? -2/3, -4/5, -6/7, negative, 2n over 2n plus 1. Well, that's not surprising because -1 is a limit point of the sequence. So we know that every interval, -1 minus epsilon, -1 plus epsilon, contains infinitely many terms of the sequence, which this does. But it fails to contain all positive terms of the sequence, actually all non-negative terms of the sequence, namely 0, 1/2, 3/4, 5/6, 2n minus 1 over 2n. So this interval, -1 minus epsilon, -1 plus epsilon, fails to contain infinitely many terms of the sequence for epsilon equal 1. So we can't say that it contains, quote, all but finitely many, end quote, terms of the sequence. So P1 equals -1 is not the limit of this sequence. Well, let's take P2 equal 1 and put it to the very same standards that we tried to hold P1 to. Okay, let's subject the limit point P2 equals 1 to the same scrutiny that we subjected P1 equal -1. And I claim that 1 is not the limit of our sequence. And to see that, we'll let epsilon equal 1. And that means that the interval 1 minus epsilon, 1 plus epsilon is equal to the interval 0 to 2. And this interval does contain a lot of the terms of the sequence. As a matter of fact, it contains all non-negative terms of the sequence. It contains 0. It contains what? When n is 2, it contains 1/2, and then 3/4, and then 5/6, and then 7/8. And let's see, in general, it's going to be n minus 1 over, no, 2n minus 1 over 2n, I guess. Yeah. So this interval does contain all non-negative terms of the sequence, infinitely many terms, which is no surprise because P2 equal 1 is a limit point of the sequence. So every term, every interval of this form has to contain infinitely many terms of the sequence. So no surprise that this interval contains infinitely many terms of the sequence. In this case, all of the non-negative terms. But there's a problem. This interval fails to contain all negative terms of the sequence. -2/3, -4/5, -6/7, -8/9. And so that would be what? -2n over 2n plus 1. This interval, 1 minus epsilon, 1 plus epsilon, 0 to 2, fails to contain infinitely many terms of the sequence, all of the negative terms. So we can't say that it contains, quote, all but finitely many, end quote, of the terms of the sequence. Now, what do we think that we can deduce from this? Every sequence that converges has a limit. The sequence converges to the limit. And that limit is also a limit point of the sequence. But a limit point of a sequence is not necessarily the limit of the sequence. So a limit point is not necessarily the limit of the sequence. And it looks like if a sequence has more than one limit point, that sequence can't converge. What we did up here seems to indicate that that's the case. Is it true that if a sequence has at least two distinct limit points, that sequence can't converge? It is true. It is true. Let's see why that's the case. Okay, here's the $64,000 question. If a sequence A sub n has at least two distinct limit points, P1 and P2, does the sequence or can the sequence converge? And the answer is no. If the sequence has at least two distinct limit points, P1 and P2, then the sequence must diverge. And we'll prove that. Let the hypothesis be given. And suppose that the sequence has two distinct limit points, P1 and P2. And since they're not equal, we'll let epsilon equal, well, I guess we'll assume P2 is larger. Or maybe let epsilon equal absolute value of P2 minus P1. Okay, that will work. Okay, we've established that much. We'll let epsilon be the distance between P2 and P1. And since the two are not the same point, they're distinct, then there has to be a non-zero distance between them. And we'll call that epsilon. P1 is a limit point, so every interval of the form P1 minus epsilon over 2, P1 plus epsilon over 2 contains infinitely many terms of the sequence. And similarly, since P2 is a limit point, every interval of the form P2 minus epsilon over 2 and P2 plus epsilon over 2 contains infinitely many terms of the sequence. And do we see where this is headed? I think so. There's a train wreck coming somewhere along the way. Okay, we're back. We had established that since P1 is a limit point, the interval P1 minus epsilon over 2, P1 plus epsilon over 2, contains infinitely many terms of the sequence. And similarly, since P2 is a limit point, the interval P2 minus epsilon over 2, P2 plus epsilon over 2, contains infinitely many terms of the sequence. And we chose epsilon over 2 because the distance between these points is epsilon. So P1 plus epsilon over 2 is the halfway point between P1 and P2. And P2 minus epsilon over 2 is also the halfway point between P1 and P2. In other words, these intervals don't overlap. The endpoint of this interval is the same as the endpoint of that interval. And the intervals are open, so they don't contain the endpoints. So we observe that these two intervals are disjoint. The interval P1 minus epsilon, P1 plus epsilon ends right here. And this is exactly where the interval P2 minus epsilon, P2 plus epsilon begins. These two intervals are disjoint. So no term of the sequence can be in both intervals. No term of the sequence can be in both intervals. And that has major consequences. We'll see what they are in just a second. So remember where we were. The interval P1 minus epsilon over 2, P1 plus epsilon over 2, and P2 minus epsilon over 2, P2 plus epsilon over 2 are disjoint, and they both contain infinitely many terms of the sequence. So where does that leave us? This interval contains infinitely many terms of the sequence, this interval, but none of these terms can be in the interval P2 minus epsilon over 2, P2 epsilon plus 2, P2 plus epsilon over 2, because the two intervals, this interval and that interval, are disjoint. So none of the infinitely many terms of the sequence that are in this interval can be in that interval. Hence, the interval P2 minus epsilon over 2, P2 plus epsilon over 2, does not contain all but finitely many terms of the sequence. So, P2 is not the limit of the sequence. Now, are we done yet? Not quite. let's see, maybe I should say it this way. This interval does not contain all but finitely many terms of the sequence. Therefore, P1 is not the limit of the sequence. Okay, I said a mouthful. We assumed that the sequence had at least two distinct limit points, and we showed that those distinct limit points could not be the limit of the sequence. Neither of those distinct limit points could be the limit of the sequence. Well, maybe the sequence has some other limit other than limit points P1 and P2. But if that's the case, that limit L must also be a limit point of the sequence, which means that we'd have P1, P2 limit points, and L, which is also a limit point. But that would mean we have three distinct limit points, and we've already shown that if we have at least two, none of the limit points are the limit of the sequence. So P1 is not the limit of the sequence, P2 is not the limit of the sequence, and if we have another candidate for limit of the sequence, that limit L is also a limit point, but it will fail the test for being the limit of the sequence, just like P1 and P2 did, and for exactly the same reason. Let's say we have some other real number that is the limit of the sequence. We'll call it P3. And essentially what we'll do is we'll go through this entire process again with the limit point P2 and the limit point L, which we'll call P3. And we'll show that P2 can't be the limit of the sequence, and L, alias P3, can't be the limit of the sequence either. So any sequence that has two or more limit points has to diverge. It can't converge. Now that still leaves some questions. We had an example, a concrete example a little while ago of a sequence that had two distinct limit points. And the terms of the sequence were alternately positive and negative. And the negative terms converged to -1, and the positive terms converged to +1. And P1 equals -1 was a limit point of the sequence. P2 equals +1 was a limit point of the sequence. That sequence had two limit points. Could a sequence have more than two limit points? Maybe 3 or 4 or 5 or 6 or 7? Think about it. Play around with the idea. And just to start off with, see if you can create a sequence that has 3 distinct limit points. And if you can do that, then try to create a sequence that has n distinct limit points for n greater than or equal to 2. And if you can do that, then wow. For any finite integer n, any natural number n, we could show that there's a sequence that has n distinct limit points. Where do we go from there? Could we show that we can create a sequence that has infinitely many limit points? Let's say countably infinitely many limit points. Boy, that would be something to show, wouldn't it? And it might be possible. First, try to create a sequence that has 3 limit points, and then try to create a sequence that has n limit points for n greater than or equal to 2. Just an arbitrary natural number n greater than or equal to 2. Then see if you can create a sequence that has countably infinitely many limit points. That would be a feat. And if you can do that, then see if you can create a sequence that has uncountably many limit points. You know what? If we got to that point, I think we would have milked this problem for all it's worth. It's something to think about, and it might be a great project for MathFest if anybody feels up to the challenge. So let's see, that was one of the questions. Can a sequence have more than 2 limit points? Apparently it can, because I'm trying to push you in that direction of exploration. A sequence that has 2 or more limit points diverges, and a sequence that converges is such that that limit is also a limit point of the sequence. And the only time that a sequence can converge is when the sequence has one limit point, and that limit point is the limit of the sequence. Is it necessarily true, though, that if a sequence has exactly one limit point, that the sequence converges? If the sequence converges, then the limit of that sequence is the one and only limit point of that sequence. But if the sequence has one and only one limit point, does that necessarily mean that the sequence converges to that limit point? That's a great question, and it's not an obvious question. There are two ways to go about this to establish it one way or another. We can try to prove that if a sequence has exactly one limit point, then the sequence converges to that limit point. Or we could play devil's advocate and try to create a sequence with one limit point, exactly one limit point, a sequence that doesn't converge. Could we do that? Let's see. You know what? I'm not going to do it. I know the answer, but if you feel up to it, I'd like you to play with it. Here's the question. If a sequence has exactly one limit point, does that mean that the sequence necessarily converges? And I guess the way to approach this is to try to create a sequence that has exactly one limit point that doesn't, a sequence that has exactly one limit point that doesn't converge to that limit point. And one of two things is going to happen. Either we're going to fail, and that will give us some insight as to why a sequence with exactly one limit point has to converge. Or if we're trying to create a sequence with exactly one limit point that doesn't converge, we'll succeed and we'll have a counterexample. So do this. Try to create a sequence that has exactly one limit point that diverges. If we succeed, we'll show that just because a sequence has exactly one limit point doesn't mean that the sequence converges. If we fail, we may gain some insight as to how to prove the statement that if a sequence has exactly one limit point, then the sequence converges. And this would be another good MathFest project. It would be a great thing to present at MathFest. We'd probably have to do some kind of construction proof. And those are good because we just don't get enough of those to do as students. So anytime we get to do a construction proof, that's good practice for us. So we have two projects from MathFest that we might want to work on. Can we create a sequence that has 3 limit points? If so, can we create a sequence that has n limit points for a natural number n greater than or equal to 2? And if so, can we create a sequence that has countably infinitely many limit points? Ooh. And if we can do that, can we create a sequence that has uncountably many limit points? That would be a great project. And then the other project is this. If a sequence has exactly one limit point, must that sequence converge? Either give a counterexample to show that the sequence doesn't necessarily have to converge, or prove that the sequence must converge if it has exactly one limit point. Both of those things are great projects for MathFest. And I do them right now, but you know what? If we're up to it and we want the challenge, both of those things would be great things to investigate for MathFest.